Let's continue with our discussion of Griffith's Chapter 1. I wanted to talk about this. This is a really important result that Griffiths goes through, and I thought it'd be good for us to go through it. And so we're taking our equation here that says if you square or take the absolute square of the wave function, integrate over all space, that's your normalization requirement. And we want to see what the time dependence of this is. All right, and so we're going to set this up, and we're going to say, okay, so we know that, say, if at time 0, this equals 1. All right, what happens if we take the time derivative of this? And so now here's one thing, the partial derivative. So it's kind of weird, but this whole statement in here, because you're integrating over x, is just a function of time. All right, and so that's why we have the total derivative outside here. Now when it comes inside, we're taking this derivative, we're attacking it directly onto the absolute square of the wave function, so it has to become a partial derivative. But of course we treat it very similar to how we're doing a regular derivative, just that we assume that the x is a constant. And so just real simple things with the derivative. When I write this out, the actual definition of the absolute squared is psi star times psi. And if I go through and just do a product rule, I get psi star times the derivative of psi with respect to t, and the derivative of psi star with respect to t times psi. All right, so that's going to be our definition. So we're going to sort of take this piece here and work with this piece, and then plug it back into that integral. Now, here are just our definitions from the time-dependent Schrodinger equation. So again, the time-dependent Schrodinger equation. And what I've done is I went through and divided by the factor that was outside here to get just the derivative term by itself. And so the first thing is you just want to make sure that you can go through and do this and that you agree with what the right-hand side comes out to be. Okay, and so if this is the statement for the derivative of psi with respect to t, then what I do is I just take the complex conjugate of both sides and I get this equation here. So again, just double check this to make sure that you agree. Basically, every I turns into a negative, and then the psi turns into a psi star because the psi could be complex. And then what we do is we just plug in these two things in here for our two derivative equations. And so here I have psi star and then derivative of psi with respect to t. And so if I take that, I take this piece over here, I get the I h bar over 2m, and then the second partial derivative of psi with respect to x squared minus I h bar, the potential, times psi. So I have that, and then I'm going to be adding, all right, this term inside of here, which is negative I h bar over 2m, this guy here, and of course that's some psi. Now what we find is when we do this, all right, these two pieces here are going to cancel out, because they're just dealing with the exact same piece just on either side. One's positive and one's negative. And so those two pieces will exactly cancel out. And so if I go through on that one, then it'll come out to be something kind of like this. So again, these two pieces cancel. And so I'll be left over with these two pieces here. And so I'll have something kind of like, I'm going to pull this constant out, I h bar over 2m. And so over here, I'm going to have psi star, the second derivative of psi with respect to x squared. And then over here, I'm going to have a minus. Now, it doesn't really matter the order you do this, but we typically always write it this way here, since these are just functions. You can kind of move them around pretty easily. I've got this piece right here. And so now if I just forward, this is the piece that I just had. Okay. And so this is the piece I just came for the side. And now they sort of do a jerk move. Okay, they pull this partial derivative out. And, you know, it's not the kind of thing that's like super obvious. And you look at this, you're like, okay, I can see how pulling that out from there and out from there works. But the problem is when you actually were, say, to apply this derivative, you'd end up using some product rules. Now what happens is that the sort of extra product rules you would produce cancel out. Okay, and so I suggest if you're sort of stuck here, actually just try this piece right here. Try taking the x derivative of this whole stuff, okay, and you'll see that it does actually come out to equal this. But again, I think it's kind of a jerk move because it's not super obvious you can do that. All right, and so then what we have here is we have this, and now remember this is what the time derivative of this psi squared was, and so basically if I take this and insert it in here, all right, now what happens is this becomes a full derivative. So by the fundamental theorem of calculus, right, if I have the integral over dx of a pure derivative here, what happens is I just end up with what I was taking that derivative of evaluated at my endpoints, which are infinity, positive, and negative. And then we look at this and we say, okay, so what happens is because both of this psi and psi star have to be well-behaved wave functions. And what that means is they have to go to 0 at all of these endpoints. So this term we have here, because of this piece and this piece, by definition, goes to 0. If it doesn't, then these things aren't valid wave functions. So our wave functions have to go to 0 at the positive and negative infinity like that. Okay, so basically what we did here is we went through, we said, okay, let's find the time dependence of this thing here. What rules the time dependence is the Schrodinger equation. So we use that to get this intermediate step, and then we use the definition of wave functions. The important thing is that if this thing is normalized, if this integral psi squared over dx is equal to 1, it'll equal to 1 for all time. And so now we'll move on to something that we've dealt with before, the expectation value. And so now we're going to look at the expectation value of x. And so again, this is the average of some measurements. Here it's position measurements performed all on particles in our state psi. And so for us here, our expectation value is going to look like this here. Just be careful, this is not the average of many measurements of the position of the same particle, but of particles all in the same state. And the format of this is very similar to the form that we were doing for our statistical problems we were doing previously. All right, and so you're basically, instead of a sum, you're taking the integral. Again, this is our probability density, and this is x. And so here you have the probability density, and the value you're talking about, j. Now, some word you'll see thrown around sometimes is the word ensemble. And all that means it's a large number of particles all prepared in the same state. So when I think about expectation value, I think about, you've got basically 1,000 experimental setups that are all the same with the particle in the exact same wave function. Okay, all 1,000 particles in the same wave function, and you go through and you try to find the position of all 1,000s of those. Okay, and all the group of those together is called an ensemble. And then if you take the average of all those position measurements, it should be pretty close to what your expectation value is. So the book then goes through and calculates the time derivative of the expectation value of x. All right, and they come up with this thing here, which they then multiply by the mass and call the momentum. And so this is, again, they're theorizing this is true. It turns out that it is true. But we're going to then use this to use and to calculate the expectation value of momentum, because we're going to find there's a relationship between between our momentum and our position that we're going to talk about. And so it turns out to be here. Just one thing, Griffiths dropped the limits of integration at this point. I'll probably do the same just because it gets kind of busy. Okay, but this integral will end up being our momentum integral. And this is an example. We've talked about this before, okay, Ehrenfest's theorem, that expectation values obey classical laws. So we saw this with the spin precessing in a magnetic field. Well, it's the same sort of thing here. Okay, so we just had an example of it here. Okay, this basically looks like our rule, if we want to do this, say, in one dimension, px equals m times vx. All right, we'll also find another version of this here, which is this case here, which is the time derivative of the momentum, which is the force, will equal the expectation value of negative dv over dx. These are both classical results. And so again, what will tend to happen is that our expectation values will obey the classical laws that we remember. And so we'll point this out from time to time. And so now the book talks about operators. We're going to spend a lot of time in class talking about this, but essentially what the book is saying at this point is it says, hey, here's how to calculate the expectation value of x, here's how to calculate the expectation value of p. If we kind of go through and massage both of these, you can get them into a shape like this here. All right, and what happens is this will be able to be done for all of our expectation values, and the book calls sandwiched. And so what that means is you have this thing in here sandwiched between psi and psi star. So over here, psi star, psi, this is the thing that's sandwiched. This thing that gets sandwiched in here, which we haven't really even talked about, but we're going to start talking about now, is called the operator. Okay, so, and we'll define that as x hat. So the x hat operator is x, and the p hat operator will be that thing down there. So again, you probably have not dealt with operators. That's fine. We're going to talk about them in class. But that's the definition of these operators. And for now, it's just something that we're sort of noticing, okay, for the most part. But we'll talk more about this to try to hopefully make a little more sense of it. But Griffiths then says, well, so as a standard definition then, we're going to find that if we know the operator for some observable, to find the expectation value of that observable, we just do this sandwich trick. Okay, psi star psi, we stick the operator inside there, and then this will be the way we can calculate the expectation value of this. So we haven't actually used this idea of operators for anything yet, so it's just something that he's sort of mentioning, and we'll sort of, again, try to flesh this out a little bit in class. So now the last thing, the uncertainty principle. And so if you look at waves, so imagine generating a wave by vibrating a rope up and down. Okay, so in this case here, if I got this nice sinusoidal type wave, it's a very well-defined wavelength, right? I could look here and just measure the wavelength from peak to peak, something like that. However, the position of the wave is much more spread out. Okay, so since we know the wavelength very well, we don't know the position. Now imagine generating a single pulse on a wave, something kind of like this here. This is the opposite case. Okay, here you have more of a well-defined position, right? The position itself is somewhere, this is somewhere in this region here, more than likely, of the wave. However, the wavelength of this wave is ill-defined. Okay, if you just look at it here, you can't really tell what the wavelength is. And so what happens is with wave phenomena, the position and the wavelength are in general two competing quantities, and there's a trade-off. So the more precise you know the position, the less precise you know the wavelength, and then vice versa. The more precise the wavelength, the less precise the position. And this is true for all wave phenomenons. We're going to use it here in quantum mechanics for a particular thing. And here's just an example to show, some of you probably haven't thought about this, but we're going to deal a lot with this semester, and it's this idea of adding a bunch of waves. Okay, and so if I take, so here I just make this little diagram here where I add 1, 2, 3, 4, 5, 6, 7 different waves. Now these waves, if you look here, they're all peaking through the middle here. So they're all adding constructively right here. These waves, though, are all different wavelengths. If you look at them, they're all different wavelengths. They're sort of just random wavelengths. Okay, and what happens is if I actually go through and add up all 7 of these, constructive and destructive interference, what happens is here at the endpoints, because it's randomly sort of done with wavelengths, the destructive interference takes over, and it's pretty much 0 on the endpoints, and you have this wave that's mostly defined in some region here. And so we're going to find that just by definition, any wave you have, whatever kind of wave phenomenon you have, you can break it down into a bunch of sinusoidal waves. And so in this case here, if I take just 7 sinusoidal waves, what happens is that's how I can build up one of the waves like Griffiths was just talking about, a little pulse. Okay, so in general, a pulse will be a combination of waves with many different wavelengths. And so this is sort of an expression of this idea that, okay, so here my delta x, the position of this wave, is much more defined. But in order to do that, okay, I had to add 7 different wavelengths. So my wavelength is more undefined than it would have been for a regular sine wave. So now for us in quantum mechanics, right, we know that from de Broglie we can relate the wavelength and the momentum this way here. All right, and so what happens is for us this relationship not just being between the position and the wavelength, is between the position and the momentum. And so this is very famous. So you've seen both Moore and Griffiths' descriptions of this, the Heisenberg uncertainty principle. So basically the standard deviation of the position and the standard deviation of the momentum, sort of the uncertainty, the spread in both of those, times each other, is greater than or equal to h bar over 2. Okay, and what that in general means is that if my, say, spread in my x is bigger, then the spread in my momentum will go smaller. Right, and so it's just what we've sort of been talking about. If I know my position really well, then I will know my momentum less, and vice versa. And so if you build a state where the spread in position is small, by making your psi, your wave function, a localized spike, the spread in momentum will be large. And so this will be a thing that happens. And look over here, this should be P for momentum, a little typo here. And we'll speak a lot about this as we go through the semester. This is an important finding in quantum mechanics, and so it's something that we'll come back to. The final thing I wanted to talk about is this is one of the questions in the PCQ. And one of the things we're going to be really interested in doing is using symmetry when we calculate integrals. This is something that you learned in calculus class, but now we really want to use it as a tool. And so if you're really good with your symmetry, okay, whether your function is odd or even about the origin, you can sometimes save yourself a lot of work. And so here's an equation. So here we're trying to find this integral, the integral of this function, e to the negative x squared over b. This is the Gaussian. You may not be familiar with this, but it looks like this right here. Okay, so it's a nice function that's even about the origin. And so if I want to integrate negative infinity to infinity of this function times our good old friend e to the ikx, all right, now I can actually find out a lot about this integral without actually doing it. And so here's the question. Is this zero? Is it non-zero and purely real, non-zero and purely imaginary, or is it non-zero in some combination? So think about this and answer on the PCQ, and we'll talk about it.